1G. In the late 1970s and early 1980s, the world saw the birth of the first commercial cellular network, a system that relied entirely on analog radio signals to connect people on the move. Before this breakthrough, early mobile phones were bulky car units operating on the mobile telephone system, which depended on massive centralized radio towers. These primitive systems could only handle a few dozen simultaneous calls across an entire metropolitan area, creating a massive waiting list for business professionals who desperately needed mobile communication. 1G solved this severe capacity problem by introducing the revolutionary concept of cellular webs, which divided large geographic areas into small interconnected cells. Each cell was equipped with its own low-power base station, allowing nearby towers to reuse the exact same radio frequencies simultaneously without causing destructive mutual interference. This fundamental change meant for the very first time, thousands of people could make phone calls from their vehicles or carry legendary brick-sized handsets like the Motorola Dynatac 8000X. These networks ran on protocols like UMTS in America or TACS in Europe, transforming the landscape of modern business communication. However, because the voice signals were sent as unencrypted analog waves through the air, security was practically non-existent. Anyone with a simple off-the-shelf radio scanner could easily eavesdrop on private corporate conversations. The audio quality was also incredibly poor, constantly filled with background static and crosstalk from neighboring cells. Users experienced frequent dropped calls whenever they crossed a boundary from one cell to another. Furthermore, these first-generation networks were completely limited to voice calls, offered zero digital data capabilities for text or internet, and suffered from terrible battery performance due to the massive physical power required to maintain an uncompressed analog connection. This meant phones could only last for about 30 minutes of talk time before completely dying. By 1991, the launch of the Global System for Mobile Communication, or GSM, in Europe marked a definitive transition from analog waves to digital bits. This technological shift solved the massive security vulnerability of the previous era by introducing robust digital encryption. The new system scrambled voice data before broadcasting it through the air, making unauthorized eavesdropping nearly impossible for casual snoopers. Digital signals also allowed network engineers to compress data significantly, meaning carriers could fit multiple distinct conversations into the exact same radio frequency slice. This was achieved using time division multiple access, or TDMA technologies, which chopped communication channels into tiny time slots. As a result, network capacity increased drastically, which plummeted the cost of mobile services and transformed cell phones from corporate luxury items into everyday consumer electronics. For the average user, this change brought crystal clear voice quality, longer standby battery life, and the introduction of the Subscriber Identity Card, or SIM card. This tiny plastic card let people instantly swap their network identity between different pocket-sized devices like the iconic Nokia 1011. Most importantly, 2G introduced the world to short message service, or SMS, alongside later packet upgrades like GPRS and Edge. These additions birthed an entirely new global culture of instant thumb-typing communication. Despite these massive leaps forward, the early versions of 2G were still built on a circuit-switched foundation optimized exclusively for voice. This left basic data speeds maxing out at a painfully slow 9.6 kilobits per second. This speed made accessing the expanding World Wide Web practically impossible, leaving mobile users completely isolated from the massive internet boom taking off on desktop computers. 3G. In 2001, the global launch of the Universal Mobile Telecommunications System, or UMTS, completely replaced the old, outdated infrastructure with a brand new high-frequency digital network built from the ground up for internet data. This evolution solved the severe bandwidth starvation of the 2G era by implementing wideband code division multiple access. This specific technology allowed multiple devices to send and receive digital data over the exact same wide radio channel simultaneously by assigning unique mathematical codes to each packet. Because of this, real-world data speeds boosted dramatically, initially delivering around 384 kilobits per second. The infrastructure eventually scaled into multiple megabits per second through high-speed packet updates, often marketed as 3.5G. For the daily user, 3G transformed the mobile phone from a basic communication tool into a pocket-sized multimedia computer. This enabled true mobile web browsing that felt comparable to a desktop computer, alongside live GPS navigation maps, mobile app ecosystems, and digital music downloads on early smartphones like the iPhone 3G. It also introduced front-facing cameras on handsets for video calling, signaling a futuristic shift in how human beings interacted daily. However, the feature was initially rarely used due to high carrier data costs and unstable connection rates. The major limitation of early 3G infrastructure was its immense power consumption, which drained phone batteries rapidly and caused early smartphones to run noticeably hot during basic data transfers. Additionally, transmitting these higher frequency signals required massive multi-billion-dollar global investments in new cell towers. As a result, reliable 3G coverage was initially sparse and took several years to deploy outside of major metropolitan cities. 4G LTE. Around 2010, the telecom industry experienced a massive paradigm shift with the deployment of long-term evolution, a revolutionary standard that completely abandoned old circuit-switching legacy hardware in favor of a unified all-IP network. Before 4G, mobile networks operated in a split fashion, where voice calls traveled on traditional dedicated circuits while data packets traveled on a completely independent layer. This split restricted overall efficiency and capped system capacity. 4G LTE solved this structural bottleneck by converting absolutely everything, including standard voice calls via Voice over LTE, into standardized digital data packets traveling over the exact same Universal Internet Protocol highway. This architectural overhaul, combined with the deployment of massive multiple antenna arrays called MIMO and carrier aggregation to bond different frequencies together, pushed the real-world mobile download speeds past 100 megabits per second. This massive speed jump completely revolutionized daily life across the globe. It enabled the rise of the modern gig economy, seamless ride-sharing applications, instant high-definition video streaming on platforms like Netflix, and competitive mobile cloud gaming with virtually no noticeable input lag. However, as billions of smartphones, tablets, smartwatches, and background applications flooded the wireless spectrum, 4G networks began facing severe radio congestion. This became highly obvious in crowded environments like sports stadiums, concert venues, or dense city centers where data would grind to a halt. Furthermore, the underlying 4G framework was never mathematically designed to handle the ultra-low latency requirements needed for instant mission-critical machine-to-machine communication. This meant it could not support autonomous vehicles responding to split-second traffic changes or remote industrial robotic surgical systems. 5G. Starting in 2019, operators began a massive global deployment of the fifth-generation network, engineered specifically to connect millions of smart devices simultaneously per square kilometer while virtually eliminating transmission delays. Traditional 4G networks were struggling to support the sheer density of IoT devices, smart vehicles, and smartphones, often slowing to a frustrating crawl during peak hours in urban areas. 5G solved this critical capacity crunch by opening up entirely new ultra-high-frequency radio spectrum bands known as millimeter waves. Alongside this, it implemented massive MIMO antenna arrays that use advanced beamforming to target data signals directly at individual users rather than broadcasting radio energy blindly in all directions. This structural upgrade pushed potential download speeds up to an astonishing 10 gigabits per second, while dropping network response latency down to a nearly instantaneous 1 millisecond. For wider society, this technological leap provided the core infrastructure needed to sync smart city traffic grids, manage automated robotic factory floors in real time, and stream ultra-high-definition 4K video content without a single second of buffering. Despite these incredible capabilities, the ultra-high-frequency waves used by high-band 5G have a severe physical limitation. They possess an extremely short propagation range and are easily blocked by everyday physical obstacles like brick walls, double-paned glass windows, or even wet tree leaves. As a result of this fragile signal nature, carriers are forced to install thousands of small, dense cellular nodes on 6G. Looking forward toward the 2030s, the next frontier of wireless connectivity aims to merge the physical and digital worlds using ultra-high terahertz frequencies. While 5G built the Internet of Things, 6G solves its looming data bottlenecks for holographic telepresence and augmented reality. By opening untapped radio spectrum, it boosts experimental download speeds to an astonishing 1 terabit per second, embedding advanced artificial intelligence directly into the core network fabric. For everyday reality, this means seamless, lightweight AR glasses, real-time smart city simulations, and instant cloud processing. However, the fundamental physical limitation of 6G lies in its extreme vulnerability to atmospheric conditions, as these fragile waves are easily absorbed by simple water vapor in the air. To survive, the architecture must integrate low Earth orbit satellites and drones to maintain an uninterrupted data blanket over the entire planet.